Okay, so we are doing harmonic functions. So there are a lot of properties we are doing. Mainly last theorem we did, which is quite a big theorem, very important theorem. That what we did. Let this recall. Let U be harmonic. Harmonic in omega. Then U is real analytic in omega. Then U is, there are a lot of many steps involved. Real analytic in omega. So the just I recall the proof just a little bit, that what is the main step? Let K be a compact set in omega. Okay, be a compact set. We want to show, if want to show real analytic, we know what is the, if and only a function U is said to be real analytic if and only we satisfy some condition, right? So what that we have done already done in the, when we are studying the real analytic functions in our Rn. So let K be a compact set, and let and set compact set, we want to show that there exists R positive, M positive, such that d alpha of ux is less than m alpha factorial r to the power mod alpha. So for all x in the compact set K, and for any alpha. So then this will imply that U is a real analytic, right? Because this is an if and only if condition. If this is an if and only if U is real analytic. That we have already studied in chapter 2, real analytic. Okay, now you just tell me, in proving this, I used a step, a very important step was the step 1. And step 1 and step 2 is quite easy from step 1, but the step 1 is very important, that if, so we have an estimate on a derivative, right, for harmonic function x naught of omega, and since omega is an open set, we can always find an R such that Vx naught R is contained in omega. Then d alpha of ux is ck. Of course, we explicitly know what the constant ck is, by r to the power n plus k, and norm of u L1 of Bx. You know what is the norm of Bx. This is nothing but, this is the integral of u over the set Bx. Right? So this is the set Bx, in norm of u L1 Bxr. Now you just, and this should hold for, and you know when mod alpha equal to k, we explicitly know the constant ck. Okay. Now you just remember what we have for the first order derivative. You remember, if you remember well, then we know that what we have in the for k equal to 1, or we have del u by del xi. If you remember well, we have proved this as an induction step is less than a constant c1 by r to the power n plus. This is a very important estimate. Please keep it in your mind. This is one of the most important estimate in harmonic function. So if u is a harmonic function in omega, then at each point the derivative will satisfy this L1 of Px naught of r. Okay, so this is a very important estimate we obtain. For the harmonic, and then we know what are the step 2 and all those things. Okay, now I said that harmonic functions resembles the analytic functions in quite a bit of analytic functions in complex analysis, right? I have already said this, right? It resembles the analytic functions in complex analysis. Okay, now I will do a theorem which is very simple. This is a new theorem. Okay, and I will use this fact. Okay, the derivative of if u is harmonic, then del u by del x at the point, any point x naught, will satisfy this estimate. Okay. Okay, now this theorem, of course, known as, famous theorem, Liouville theorem. Can anyone tell me what is the Liouville theorem in complex analysis? Just, just remind me the statement. Can anyone?
Any entire function which is bound.
Yes, yes, go ahead. Yes, go ahead. Please. Yes. What happened?
If entire function and its mode of f is less than equal to a plus b mod x raised to power n, then f is a polynomial of
No,
degree n.
that is I'm asking just a simple Liouville theorem. If u is an entire function, it is bounded, then u is what?
Constant.
Yes, that's all. So here also the same Liouville theorem holds. Okay, it's a beautiful theorem. Any bounded harmonic function on Rn is a constant. Okay, is that okay? Same statement holds here. Any bounded harmonic function on Rn is a constant. Is that clear? How will you prove? Anyone? How will you prove?
From last inequality.
From which one? This one? This one?
Yeah.
Yeah, very good. Yes. Let U be harmonic in Rn. Okay. Then you can for each point x naught this. Then for any x belongs to Rn and R positive, there holds is del U by del xi at the point x is less than a constant C1 R2. Just you recall this estimate. Okay. R1 R to the power n plus 1 integral bxr uy dy. Now what I will do? Then what I will do?
Like u is bounded, so we can this further is again bounded by
Less than, yes. Supremum over u over Rn, right? C1
yes.
by R to the power n plus 1, the modular b of xr. Yes? Yes or no?
Yes.
So del u by del xi at the point x is less than what I got. What we get is suprema over u over Rn, of course, because we know that this is bounded. C1 by R to the power n plus 1, the measure of bxr. Yes, these I can write. Supremum over Rn C1, we know that the measure invariant. So it is B0R. Yes or no? Now I can use the scaling. This is equal to suprema over U R to the power n C1 R to the power n plus 1. What will be this? R to the power n into measure of B01. Yes, just scaling R by, you just put ball of radius R, you can scale by, you can just take X to be R, Y by lambda, Y by R. So it will be a measure, then in Y coordinate it will be a ball of measurement, but the measure will change as R to the power n B01. Yes or no?
Yes.
This is a constant, a measure of ball of radius 1 and centered at 0. It's a constant. This supremum is m, let's say m, which is bounded. So m C1, this n and n cancels out. This is alpha n by R. Then what I will do? Now taking this should hold for every R positive. Now taking are increasing to infinity, and we get that what I will get, that uxi at the point x equal to 0. Since x is any arbitrary point, any arbitrary point in Rn, this imply, what does this will imply? U equal to constant. This is a famous Liouville theorem for harmonic function, that any bounded harmonic function on Rn is a constant. So what is the main idea? Main idea is this estimate. And where this estimate comes, again, you should know that these estimates come. If you see the proof, it's the main idea of all the proofs will be, all the proof lies inside the proof of idea of mean value property. That if V is an harmonic function, U is an harmonic function, then U satisfy mean value property. This is the main thing you should say. Mean value property. Okay? Like where it is in complex and is the Cauchy integral formula. Okay, good. Now I will do another very important. You have again this theorem you have seen in complex analysis, maximum modulus principle. Here it is called maximum principle. Maximum principle. Okay, this is very important. Can just tell me? Can anyone tell me what is the maximum modulus principle for complex analysis? In complex analysis, just recall. If U is an analytic function, can anyone recall?
Maximum occurs on the boundary.
Exactly. Very good. Very good. Here also the same things will work. Okay. There are two theorems. Let omega be a connected open set, not necessarily bounded. Okay. Any connected open set. Okay. Connected open set. Set in Rn. And suppose a harmonic function u, okay, u attains its supremum in omega, then u is a constant. Since omega is an open connected set, so this first statement says that if u is an harmonic function, it attains its supremum in omega. That means in the interior point of omega. If u attains its supremum in an interior point of omega, of course all the points are interior point for omega, then u has to be a constant function. Okay. And the second, as you said, let omega be a bounded. This is important. Okay. Bounded open set in Rn. Then for any harmonic function u on omega with u belongs to continuous up to the boundary. That means u is also continuous, not only in the interior of omega, also with the boundary. Okay, up to the boundary. This means the maximum of u on omega closure is equal to maximum of u omega. Since u is continuous function up to the boundary and omega closure is a compact set, you know that u attains its supremum, right, in omega. Yes or no? Since u is a continuous function up to the boundary, this omega closure is a compact set, it's closed and bounded set in Rn. So it's a compact set, and we know that if u is a continuous function on a compact set, then u attains its supremum. U is, first of all, u is a bounded function. U will be bounded and attains its bound. Okay, and there it says that sorry, maximum what? It says that the maximum will attain. This equality will says that, because if the maximum attain at the bound at the interior point, then from the previous first theorem from part 1, it says that u has to be necessarily constant. Yes or no? Because we don't. Yes or no? Suppose u the supreme, because we know that u is a continuous function of the compact, so that means it u attains its maximum, right? Suppose it attains its maximum at the interior point, some point in interior of that is a omega is an open set, some point in omega, then automatically by the previous theorem, theorem 1, the part 1, it says that u has to be a then u has to be a constant, then everything is equal, because u is a continuous function, you cannot have a up to the constant, u is equal to a constancy up to the boundary, right? But this theory says that this is more, it will attain at the boundary. If it attain at the interior point, then it has to be constant. Well, of course, this does nothing violates, because it is equal to the maximum of del omega, because you will be u equal to constant at the del omega also, right? Because u is a continuous function, right? So, but it says that you will attain this maximum at the boundary. Okay, so let me prove this. First of all, I prove that if it attains its supremum in omega, then u has to be a constant. Okay. Any idea how to go forward? Anyone? Just recall the idea from complex analysis. Any idea? Any idea how to begin with the proof? Some. Hmm? Any idea? Okay. So let omega 1, I define a subset of omega. How I define? X belongs to omega such that u of x equal to maximum of u in omega. The first one I am proving. Okay. So what is this? Omega 1 is a set of all x in omega such that it attains the maximum. Okay. Is that clear? Now I suppose, because it says that if u attains its maximum or the supremum at interior, so suppose omega 1 is non-empty. Let x naught belongs to omega 1. What does it mean? These imply u of x naught is equal to maximum of u in omega. Okay, so like this. So this is your omega. It's not a point x naught. It says that at the point x naught it attains its maximum, and x naught is an interior point. Okay, so let R such that b x naught R is contained in omega, like this. To find R such that this is omega of the whole set contained in omega. Okay, then you apply the mean value property. What it says that u of x naught is equal to 1 by ball x naught R b x naught R uy dy. Because u is a harmonic function, at each point x naught I can write in terms of the average by 1 by bx naught, the measure of this one, right? Just by using mean value property. Now this implies 1 by bx naught R integral over bx naught R uy minus u of x naught dy equal to 0. Since this is not equal to 0, because R is a positive, so bx naught R is always the measure is a non-zero measure. So these imply integral bx naught R uy minus ux naught dy equal to 0. Okay, now you just observe, note that what is ux naught? What is ux naught? Ux naught is a maximum of u over omega. That means u is always less than ux naught in omega. In particular, uy is less than equal to u of x naught for all y in bx naught r. Okay. This is, let's say, equation 1. This is, let's say, equation 2. So 1 and 2, what will the what should one can get from these two implication? Anyone? Uy is always less than ux naught. That means this gives you uy minus u of x naught is always less than equal to 0 for all y in bx naught r. So then, and this is given the integral is 0. So from 1 and 2, what we can conclude?
uy is ux.
Yeah, because you remember, if f is a continuous function in the open interval or a closed interval ab, closed interval ab, integration a to b fx dx equal to 0, and f is non-negative, this implies f is identically 0. Yes, just the neighborhood property of continuity. U is a because U is a harmonic function. That means U is a C infinity function. In particular, U is a continuous function. 1 and 2 implies that U of y is identically equal to U of x naught for all y in B x naught of R. Yes or no? Is that clear? So again, I am writing. So U of y is identically equal to U of x naught for all y in B x naught R. Is that clear? What does it imply? This imply B x naught R is contained in omega 1. Because you just remember what is omega 1? Omega 1 is set of all x in omega such that ux is all the maximum of u in omega. Yes. So bx naught R, because uy is ux naught for all y bx naught. These imply bx naught is contained in omega 1. So and x naught is arbitrary. X naught is arbitrary. So this imply what this imply? What can you say about the omega 1 set? Can anyone tell me? What can we say about the
Open set.
Yes, omega 1 is an open set. Is an open set. Okay. Is the omega 1 closed? A continuous function set of all x such that fx equal to some constant. Maximum of u in omega suppose is constant. Omega 1 is also a closed set. Straightforward. Yes or no? It's a closed set, right? Omega 1 is a closed set since u is a continuous. Yes or no? Yes or no?
Yes.
Yes, sir.
So these imply omega 1 is closed as well as open in omega, and omega is connected. So what does it imply? What does it imply? Omega 1 is closed as well as open in omega, and omega is connected. What does it imply?
Omega 1
Either
equal to
empty or
omega.
whole omega.
Exactly, it's either empty. So because already if u attains its maximum, right? Either omega 1 is empty or omega is omega. Clear? Is that clear?
Yes.
Okay. So u is a constant if you add. Number 2, can you just anyone tell me how the number 2 part 2 will follow immediately? Can anyone tell me how part 2 follows immediately? Just from here. So this I have proved now. Part 2, can you say that why it follows immediately? First inequality is immediate. Omega closure contain del omega. That implies maximum over O in omega closure is greater than equal to maximum over U del omega. Now you tell me the opposite one. Can anyone tell me why is immediate? Why it's immediate? Suppose U attains its maximum in omega. That is omega closure minus del omega. Then u is necessarily constant. Necessarily constant. And of course, maximum of u for this case, equal to maximum of u del omega, as u is continuous. Up to the bound. Sorry, u is continuous up to, that is why I have hypothesis, because we know that u is c infinity in omega, but we don't know up to the closure. So it is given that u is continuous up to the boundary. Here it is. So this immediately implies that, so maximum has to be on the boundary, right? So one can write immediately using this and this, that omega closure is equal to maximum of del omega. So if u is a harmonic, so the crux of the matter is, if u is a harmonic function, then its maximum will always attain at the boundary. Of course, same will hold for minimum also. Okay, the same, just I tell you a remark. If it attains its minimum, same statement, holds for minimum as well. ठीक है? Is that okay? Is that okay?
Yes.
Okay. Now I will do so. So just have a look what I have done till now. Is that okay? Yash, Atharva, Shami,
Yes.
Vivekanand, Kritika,
Yes, sir.
Ankit,
Yes, sir.
Ashish,
Yes, sir.
Sushil, Navneet,
Yes, sir.
Sagar, Shivani.
Yes, sir.
Is that okay? Chitram,
Yes, sir. Yes, sir.
Biswa,
Yes, sir.
Annu.
Yes, sir.
Okay, so just I'm tell you, these harmonic functions are very much similar. The properties are very much similar with the analytic functions you've studied in the complex analysis. Okay, of course, this is both are quite different, but there are many resemblances of in their properties. Okay, now I will be doing known as the Harnack inequality. Okay, this is called Harnack inequality. Harnack's. Okay, Harnack inequality. It's a very important inequality in harmonic. This is used in harmonic analysis, PDE, geometry, everywhere. This inequality. Of course, what I will do is a very simple one. It can be much more generalized. Okay, it can be generalized in a much more generality. Okay, but what we will be doing is a very simple one. Okay, very simple one. Okay, you can see if you study PDE or harmonic analysis, these inequality will be every day. It will come to your research if you work if you do some research in harmonic analysis, PD or differential geometry. Okay, so these harmonic inequality will come every day. So this is so important. Okay, but of course what we will be doing is a very simple one. Okay, so let omega be an open set in Rn. Set in Rn. Then for any compact connected set K, in omega, there exists a constant which depend on the compact set K. That's all. It will depend on the compact set K, positive, such that maximum of u, you can estimate maximum of u with respect to the minimum of u. Ck, a constant which depend only on the compact set, minimum of u. First of all, you have to understand what is this. What is this? Holds for these inequality holds for all harmonic function u in omega with u non-negative. Is that okay? Let's first of all you have to understand the statement. Then we will understand the proof. Okay, proof is not that difficult. First of all, you have to understand what is this statement and why it is so important. Okay, so let omega be an open set in Rn. This is clear. What is an open set? You know. Then you take any compact connected set K in omega. Okay, you take any compact set in omega. Okay, then you fix that compact set K. With respect to this compact set, there exists a constant K which depends only on the compact set. Here is the main stress point. There exists a constant K, C which depends only on the compact set, such that you can always estimate maximum of u is less than Ck minimum of u. And this should hold for, of course, for all those u or for all harmonic function with which are non-negative. Is that clear? Or all harmonic function u which are non-negative. Okay? Is that clear? Okay. Now you tell me, u is a continuous function because u is a harmonic function. So u is a continuous function. Because u is a harmonic function, that means u is a C infinity function, and hence u is a continuous function in omega. Now you are taking a compact set K. Then of course maximum of u attained. Yes or no? Maximum of u on a compact set attained. Yes or no?
Yes.
Minimum of u on a compact set is also attained. Yes or no?
Yes.
Then you can always, this is some number, maximum of u is a compact, some positive number or something number, some number, some non-negative number, and minimum of u is also some non-negative number. You can always, these are the two number, then you can always find a constant C such that this happens. Yes or no? You understand what I am saying?
Yes, sir.
U is a continuous function on a compact set, Ck. Then of course maximum of u at compact set some number u at some x naught. Okay, u of x1, let's say. Maximum of u compact set equal to u of minimum, sorry. Minimum of also at on a compact set of u of x2. Some number, this belongs to some non-negative real number r plus. This is also some r plus. So these are the two real numbers, right? So non-negative real numbers. So there is always a constant. We can always find a constant C such that u of x1 is less u of x1. The maximum is less than a constant u of x2. Yes or no? Of course, this C is a depends on compact set K. Yes or no? Huh?
Yes.
Then what is there in this inequality? What extra I am getting? Then this is a trivial inequality. It must be a trivial inequality, right? But why this is, we are calling a Harnack, and I always say that this is one of the most beautiful and most important inequality in analysis. So why?
A constant is independent of u.
Exactly. Excellent. If you see here, these constants depend on the compact set as well as the function u. So this is true. If this ux1 is less than a constant c which depends on k, the compact set, and u of x2. These you can always get. These constants, if we do it in a very simple way, that u is a continuous function on a compact set, so it will attain its maximum, it will attain its minimum. So then let's say u of x1, u of x2, then you can always find a number c such that u of x1 is less than c times u of x2. But these constants always depend on the compact set k as well as the function u. It is not independent of the function u. But this beautiful theorem of the Harnack inequality says that if it is a harmonic function, you could get a constant which is independent of the function u. It only depends on the compact set. So if you get a compact set, just if you get some compact set k, there between any x point and let's take any y point, there always exists a constant c which only depends on the compact set, not on the function u, such that you can always write an u of x is less than some constant is of y. This constant c does not depend on the function u. This is the most important part. That is why this inequality is so powerful and so beautiful, and one of the most important inequality in analysis or in PDE, harmonic analysis, differential geometry. Okay, this is known as the Harnack inequality. Do you understand why I am stressing on this? That this constant is independent of the function u. It only depends on the compact set k. Is that clear? Is that clear, all of you?
Yes.
Very good. Very good. Okay, now let us prove this. Proof is very simple, not very hard. Okay. As I always said, of course, always use mean value property. Okay. Proof. Choose R positive such that 0 less than 4R less than distance between k and del omega. Okay, like say this is your del omega. This is you have a compact set k. What is distance between? This you know, the minimum between the two sets. So let's say this is the distance between k and del omega. Okay, you choose R such that the 4 times of R is less than k, or in other words, R is less than distance between k. This is, you know why I am doing this. You will understand immediately why. 4 is not a matter. You can take 1,000, 2,000, 3,000, anything. Okay, whatever, 1 million, 2 million, 3 million, whatever. This 4 doesn't matter. Okay, whatever. Now let us consider to any 2 point. Let x comma y belongs to a compact set. Okay, let's say here x, here y. Okay, so this is your compact set. Okay, so here x, here y. Okay, with what? So there should be not any xy I am choosing. Let xy belongs to k with x minus y. The distance between x and y should be less than r. So this distance should be less than r. Okay? Is that okay? Okay. Now you write down u of x. Again using, you know that if so this x you take 2r. Okay. This is, let's say, 2r. This distance is, take a ball. This is a ball of radius 2r. Around centered at x. So it will definitely, is this ball inside omega? Is this ball B of x 2r lies inside omega? Yes or no?
Yes, sir.
Why?
Because the distance of compact set from the boundaries is at most 4R.
Exactly.
At least 4R.
Exactly. Good. That is why I have taken. That is why I said you take 1,000, 2,000 million, whatever. Okay. Now B of x 2r, and of course this y also lies inside the ball, right? So this is bx 2r uz dz, let's say. Okay. So just a minute. I write down again by mean value property. Bx 2r bx 2r u of z dz. Okay. So here is your x, here is your y. This distance is less than r. You take this distance as this distance as 2r. You take a ball of radius 2r. This is your ball of radius 2r, centered at all. Okay. Okay. Now you just think, is that true? B of x to r, and if I take y of radius y of centered at y and radius r, you consider a ball of center at y, radius r. Is by contained in bx to r? Yes or no? Yes or no?
Yes.
Because bx to r, distance between y and x is less than r. So if you draw a ball, this ball by r should contain in bx to r. Okay, the triviality. So first of all, I do this. This I can do 2 to the power n bxr. This I can do. Yes or no? Measure of bx2r I am writing is equal to 2 to the power n b of xr. Is that measure of bx? Is that true? Yes or no?
Yes.
So this integral is bx2r uz dz. Now we know that u is a non-negative harmonic function. This set bx2r is by is contained in bx2r. That means this is greater than equal to 1 by 2 to the power n 1 by b xr. Instead of xr, I can change the center at yr. The measure will be same because translation invariant. Yes or no? It is translation invariant. So b y of r uz dz. You understand the step? Y greater than equal to, because u is a non-negative function and bx2r is a bigger set than byr. So the integral will be monotonic. So b integral over bx2r is greater than integral over byr. Right? Now you see that bxr, the measure of bxr is equal to measure of byr because Lebesgue measure is translation invariant. Yes or no?
Yes.
Now what I can write, this is equal to
UI.
exactly 1 by 2 to the power n into uy. Okay, so this imply what I have proved. What I have proved is that u of x is less than, sorry, greater than equal to 1 by 2 to the power n into uy. Okay, and this imply this, that u of y is less than equal to 2 to the power n into u of x. Okay, so in any compact set x and y of radius less than r, when the distance between x and y is less than r, and of course this is a compact set K. Okay, now I have to do the for all compact, for all a compact. So see, this does not depend on anything. Okay, now you tell me what next step, what I should do. Any 2 points I have estimated it. Now I have to do it for a compact set. What I should do? Yes.
So we can take a finite cover of balls.
Exactly. Of radius r. Yes. If x and y belongs to the compact set with distance between x and y less than r, then we obtain that u of y is less than 2 to the power n u of x. Now k is contained in I equal to 1 to m bxir. Okay, you can have x1 x2 x1 with radius r. Okay, such that bxir intersection bxi plus 1 comma r is not equal to 5. You understand what is the meaning of that? So this is your compact set. Let's say x1, let's say x2. If you take the ball, this ball like this. Okay. So there might be intersection is non-empty. Okay, such that pxi and xi plus I for is non-empty. You choose this like this. Okay. Therefore, for any xy belongs to the compact set K, then ux is what I can write. Can anyone tell me? For any 2 point of radius less than r, we have 2 to the power ux. Right? Now what I can write? If you take any two arbitrary point xy in a compact set, you don't know whether now the distance is less than r or not. What I can write? Hmm? Just think what I can write. For any
M times 2
very
of
nice,
n.
very nice. 2 to the power m into n. Clear? Because if you take the compact set K, suppose you have taken x here, y here. So if you have a ball like this, all intersecting. So you get less than r, you get here, you get here, you get here, you get here, you get here. So at max you can reach at y as m steps. Yes or no? Like this you have, like this you have, like this you have, like this you have, like this. Ux is less than ux1, x1 is less than x2, x2 2 to the power n1. Number of m, so x1 x2 x1 is 2 to the power n, x1 to x2 is 2 to the power 2 into n into x2 less than u to the power. So now maximum number it can have m because we have m number. Is that clear? Is that clear? Yes or no?
Yes.
So 2 to the power m into n u of y. Okay. These imply for all x in a compact set. These imply maximum of u over compact set is less than immediately 2 to the power mn minimum over k on m. See, this is a constant your ck, which depends on the compact set. Because why it depends on this? Because of this number m. Because it depending on the compact set, you will have a cover. Okay, you have a cover. So it depends. The constant k only depend on the compact set, not on the function mn. Okay. So as an important corollary, one can immediately get is the following. For u is a harmonic function, u is harmonic. U is non-negative, then we have by Harnack 1 by ck ux is less than u of y. So at any 2 point can be estimated from upper or lower for all xy in the complex. Why can anyone tell me why this corollary holds? Because maximum u. So u of x is less than equal to maximum of u, which is less than ck times minimum of u, which is less than ck times u of y. So u of x is less than ck times u of y. Clear? One-sided get. You just put here 1 by ck and you can get the other way around also. Okay. So the Harnack inequality, the main stress of this Harnack inequality is that any 2 point xy can be estimated with respect to u can be estimated with respect to y. Y can be the value of u at the point y can be estimated at that. The Harnack says that inside a compact set, any 2 point can be estimated. The value of u at any 2 point can be estimated upper bound and lower bound with both sides. Okay. So ux is uy is less than some constant time uk. But you should be very careful that it has to be a compact set. If you cannot do it any arbitrary point xy in a domain omega. No, not at all. You have to fix the compact set. Then inside that compact set, you can estimate the value of u in any 2 points with respect to this, with respect to u, and of course with some constant which depends on the. So if you change the compact set, then there will be a constant k1. If you change another compact set, then there will be a constant k2. So you has to be very careful that you can do for a fixed compact set. You, for a harmonic function, non-negative harmonic function, you can always estimate any 2 points. Is that clear? Is this Harnak is clear?
Yes.
Oh, okay. That is all. Not all. Most of the important theorems we have done for harmonic function. Next, our goal is to study the Laplace equation. That means next goal is, of course, again these harmonic functions, properties of harmonic function will come into play, but we will now study the Laplace equation in more generality. Can anyone tell me what do I mean by the more generality? That means we will study equation Laplacian of u equal to 0, or now I will study Laplacian u equal to f. This is called Poisson. This is called harmonic functions. When f is non-zero, Laplacian u equal to f. For a given f, we want to solve Laplacian u equal to f, and this is called Poisson equation. Poisson equation. Okay. Till now we have studied some of the property of Laplacian of u equal to 0. Now we want to study these. We want to study Laplacian of u equal to f, where f is non-zero function. That is, this equation is known as the Poisson equation. Okay, Poisson equation. Now my first question is, of course, to study this we will take some help from this. From 0, Laplacian u equal to 0 will play a very important role in the study of Laplacian of u equal to f. This is called homogeneous equation. This is called non-homogeneous, because the source term, this term f is non-zero. Here the term is f is 0. So there should be some I will use some properties. I will explore some of the properties of harmonic function to study the Poisson equation. Poisson equation means Laplacian u equal to f. So understand? Okay. First immediate lemma is, or a simple lemma is how I can convert to a Poisson equation. Let's see. Of course, first question is Laplacian u equal to 0, right? In Rn. You know there are some. So what are the functions? It satisfies, as you say, u is a constant function, u is a linear function, and all those things. First question you should ask is whether for any given f, f is given. This is a source term. F is given. For any given f where non-zero, Laplacian of u equal to f is solvable. That means always does there always exist a u such that Laplacian u equal to f? For any given f, there always exists a u such that Laplacian u equal to f? This is the primary question you should ask. Because as you know, in Rn, Laplacian u equal to 0, we know that there are some constants. To solve this equation, first of all, you have to see whether there are some function which satisfies this equation, right? So u is a constant is always that type of functions. But now the question is that always for any given f in Rn, whether you always have a solution, Laplacian u, that means you always have a Laplacian u equal to f, always have a solution? The answer is very tricky. Not always we'll have this. Okay, we will see one by one. Okay, but you should ask this question. Okay, the lemma says that let omega be a bounded domain. Then the problem u is some constant function on del omega has at most one solution. If the solution exists, then it has to be one unique solution. It might possible that this equation has no solution. It might possible. We'll see some example. At most one solution. That is why I said at most. Okay. If the solution exists, then it has to be unique. If it might happen that there does not exist any solution. One solution. Can anyone tell me why? Hmm? Hmm? That is some uniqueness I am proving, right? If it has a solution, then it has to be unique, and it might possible that it has no solution. That is the difference. That is why I use the term at most one solution. Can anyone tell me why? Suppose U and V solve the okay. Then what Laplacian U minus V will satisfy anyone?
To 0.
And what will be U minus V on the boundary? Huh? What will be the U
0.
minus 0? Good. That is, if you let W equal to U minus V, Laplacian W equal to 0, you get just from the above in omega, and W equal to 0 on del omega. What can I say now? Use maximum principle. I can use maximum principle. So this is a harmonic, W is a harmonic function in omega. Yes or no? Omega is a bounded open
Yes.
set. So maximum of W omega closure is maximum of W in del omega. What is maximum of W in del omega?
0.
0.
Good. So this imply maximum of W closure is equal to 0. What does it mean? This imply W for any point in omega x less than 0 for all x in omega. Yes or no? Wx is less than the maximum of W in omega closure, which is equal to del. This imply U minus V is less than equal to 0. This imply U is less than equal to V. Yes. Similarly,
Yes.
we can choose W tilde as V minus U. Okay. Again, Laplacian W tilde equal to 0 in omega, and W tilde equal to 0 on del omega. Use the maximum principle. This implies W tilde is less than 0. This implies V is less than equal to U. This is 1 in omega. This is 2. So 1 and 2, what I will get?
U equal to V.
U equal to V. That means if solution exists, then it has to be unique. Just using maximum principle, it has to be unique. For the equation Laplacian U equal to F and U equal to G. Okay. Of course, now we will see when it has a solution, when given F and given G, it will always have a solution or not. That is a different story. But if it has a solution, it has to be unique. That is why I use the term. I use the term at most. Okay. Now some small definition. Then we will see how to solve this type of equation. Laplacian U equal to F and U equal to G when it is solvable. First, small definitions. Okay. This is called, you know, already know that this is called boundary condition, right? E equal to G on del omega, right? This is called boundary condition. Definition. The boundary condition U equal to G on del omega is called Dirichlet boundary condition. Okay. Dirichlet boundary condition. This type of boundary. There are sometimes it will be like this. Laplacian U equal to F. Del U by del U is given on the boundary is G, not U. Okay. In omega on del omega. Okay, instead of U equal to G given, it is given that del U by del U equal to G. Okay. This type of boundary known as this type of boundary condition is known as Neumann boundary condition. Okay. Neumann boundary condition. Okay. There are some this mixed type of, suppose this type will can Boundary condition of the following: del u by del nu plus some constant u equal to g, or a belongs to r on del omega. So this is also involved, u equal to also plus. This is known as Robin boundary condition. These are just definition. We will see one by one. Robin boundary condition. Okay. We will, in this course, we will be sticking to only Dirichlet type. Okay. For this course, we will only be sticking to this Dirichlet type boundary condition. That means this type. Laplacian equal to f, u equal to g on the boundary. Okay. Sometime I will use del u by del nu, but mostly Dirichlet. Okay. But of course, we will not do this Robin boundary. But this is just for your information. This is called Robin boundary condition. Del u by del nu, you know, this is the boundary. So boundary, this nu is the unit normal. This nu is the normal. Del u by del nu is the derivative of u along the normal to the boundary. Okay, that is the del u by del nu. Okay, you know this. Now, because this type of thing comes, solving boundary problem. Solving. Suppose you want to solve Laplacian of u equal to f and u equal to g. On omega, omega is explicitly given like this: AB cross CD. Okay, and you know what is the boundary, u equal to g on the boundary. So this is your domain. You want to see A, B, C, D. You know what is that. C, D. And this is your boundary condition. A, B, C, D. This is your domain omega. What type of solution you will should expect? Anyone tell me? Can anyone tell me? Any symmetry? Is there any symmetry in the domain? Yes or no? Is there any symmetry in the domain? This is a square or a rectangle. There is some symmetry, right? What type of symmetry? Then we can look for solutions of the type u of xy is equal to. Can anyone tell me? Suppose this boundary is given. We want to solve this type of PDE. What type of solution one should immediately think of it? Anyone? Huh? Just think. What is the natural idea? This is not I'm not saying any theorem or something. What should be the natural idea? Suppose your domain is given like square. Now you want to solve this type of equation, Laplacian equal to f or equal to g on the boundary. What type of solution you should look for? Huh? Very natural. Huh?
fx times gx.
Exactly. Fx times gy. This is called
Gy.
this you have studied, no? Separation of variable. Separation of variable. Separation of variables, right? We can separate because due to the symmetry of the domain. Of course, not your life may not be that simple. Life, this omega can be very complicated, but I'm just giving you an example. Suppose your omega is like that, AB cross CD, then one can look for a solution of the form fx into gy. Then you solve what fx satisfy, what gx satisfy, what fx satisfy in the boundary. That is a difference. Then you solve it separately. But this separation of variable will play important role if your domain is like AB cross CD. Okay. Now, let me another symmetry. Go for a symmetry. Just recall an exercise I have given in the tutorial sheet assignment. Laplacian is invariant under orthogonal transformation. You have done this, right? It has been done. Yes or no? If O is an orthogonal matrix, define V of x is U of OX. Then Laplacian of V is Laplacian of U at the point O of X. Yes or no? You have done this, right? Yes or no? Yes or no?
No, sir.
No, sir.
I have given you exercise, right? Assignment I have given you.
Yes, sir.
Assignment number 2. Did you receive that?
Yes, sir.
You haven't seen the assignment? Problem 1?
Sir, I haven't solved it.
Uh-huh.
I haven't solved it yet.
But the, last tutorial class, the tutorial tutors didn't solve this. Yes or no? Ekansh, what happened?
Sir, there was no class last Friday.
Oh, there is a holiday?
So,
They
sir,
are
maybe
mid-sem.
because of the
There's no
presentation.
class like
Oh, midsem was there?
Actually, mid-sem presentation was scheduled on Friday
Oh,
itself.
yes. Sorry. Okay. Sure. I understand. Okay. Anyway, you will do it in this Friday. Okay. Okay, this we will do in this Friday. Laplacian is invariant under orthogonal transformation. That means if O n orthogonal matrix, you know what is the orthogonal matrix, right? I define V of x is U of composition OX, then Laplacian of Vx is this. Yes, this is a very simple. This is not a difficult one. Orthogonal matrix. Now consider this problem. Okay. Consider the problem. Minus Laplacian of U equal to F in BR, U equal to G on del BR. Domain has a symmetry. The ball, this ball has an orthogonal symmetry. Domain has a symmetry. Has a symmetry. Okay. So this is the boundary. It is given U equal to G. Let's say ball of radius. We want to study minus Laplacian U equal to F in PR and U equal to G on del PR. What type of and F is given to be a radial function? If F and G both are radial function, F and G. You know what is a? Can anyone tell me what is meaning of a radial function? BR in Rn. F and G are radial function. Does it mean to F and G are radial functions? Huh? Can anyone explain me why? What is the meaning of that? Huh?
so they depend on mod x rather than
Exactly. F is a function in Rn, but it will be f of mod x. Okay. Similarly, g of x should be g of mod x. It depends on the radius. That means this is your x. The value of f at the point x is equal to the value of all the point mod x. This is your distance mod x. So the value of x1 here, x2 here, both the value are same. That means on a circle of mod x equal to r, f has a. So it only depends on the, not on the angle or something. It only depends on the radius. So f, sometimes it is written as f of r, g of r. Okay, fx equal to f of mod x. So now you say f is a radial function, g is a radius. So g is the same. G will take a constant value on the radius r because g is a radial function. Okay. The domain is also has a symmetry, radial symmetry. Orthogonal transformation make br to br, right? Orthogonal transformation br to r. It will be some br, right? Now you tell me what type of solution one should expect. What type of function?
radial.
Yes, because your domain is radial, the given data f is the source function is there, g is radial, the domain is radial, so one can look for a radial solution. Okay, let's see what kind of. Then we can look for radial solution. Then can we compute Laplacian of u in terms of radial coordinate? Do you know, anyone know in terms of radial coordinate? How Laplacian will look like if u is radial? That means u of x is given to be, I write down u of mod x, but it is always good to write some phi of mod x. This is an abuse of notation. I write ux equal to u of mod x because u is a function of, so one should write that u of mod x, or you can write u of mod x also. You understand this point? Yes or no? Because this domain is x, this domain is mod x, means 0 to r. So domain of the two functions are different. We should not write u the same, right? Because the function means it depends. When we define a function, is the functional value and its domain, right? Both the domains are different, so one should not write u same way, but one can write. This is called abuse of notation. It is better to write phi of mod x. You understand what I mean to say?
Yes, sir.
Now what is del u by, so I want to compute Laplacian u in terms of phi. Okay, what is del u by del xi? Can anyone tell me quickly? Phi prime of mod x into this is mod x equal to r. So this is phi of r. Del r by del of xi. What is r? R is x1 square plus dot 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 xn square to the power half. So del r by del xi is 1 by mod x into xi. Okay, you just compute. So this is mod x xi by mod x. This is del u by del xi. Okay, so del u by del xi is nothing but phi prime of mod x, or you can write r xi by mod x. What is del square u by del xi square? Anyone? Quickly. Phi prime of double prime of mod x into xi square by mod x square plus phi prime of mod x. What will happen? Del u by del xi 1 by mod x minus xi square mod x cube. This is mod x r. So this is phi double prime of r xi square by r square plus phi prime of r 1 by r minus xi square by r cube. Okay, is that okay? Now I am to take Laplacian of u. That means summation I equal to 1 to n del square u by del xi square. That is phi double prime r by r square summation xi square plus phi prime of r 1 by r summation, that will be n by r minus 1 by r cube xi square. Okay, if I take the summation, because this is a constant, you just think phi prime r 1 by r, there is summation I equal to 1, so n will come, right? Yes or no? So what is xi square? Xi square is r square. This is r square. What I will obtain? Laplacian of u is phi double prime r to r square by r square plus phi prime of r n by r minus r square by r cube. This is r square, this is cube, r square by r cube, n by r, this is r square, this is r square. So this gets cancelled, this two gets cancelled, so this I get phi prime of r plus phi prime of r n minus r minus 1 by r, right? So this imply phi double prime of r plus n minus 1 by r into phi prime of r. Clear? If u is radial, then Laplacian of u is nothing but, sometime in the book it is written there, you will see u double prime of r plus n minus 1 by r into u prime r. But this isn't something abuse of notation, because you understand what I mean. So you can write phi prime some function, or you can write u also. This is just an abuse of notation. So Laplacian of u in radial coordinates, if u is a radial function, it is phi double prime r plus n minus 1 by r into phi prime of r. Is that clear? Is that clear, all of you?
Yes, sir.
Yeah. Okay. So what this equation now is Laplacian minus Laplacian of u equal to f on del br and u equal to g on del br. In radial, if we look for a radial solution, if we look for radial solution, that is, then it will be minus phi double prime of r minus n minus 1 by r phi prime of r is equal to f of r, u of capital R, because at the boundary, is equal to g of r. Okay, another thing it will be, right? So if r, it will be u prime. This you will understand later. Because if you see this r not equal to 0, because r not equal to 0, then phi prime of r plus n minus 1 by r phi prime of r. Clear? Is that clear? So this you will later understand. So at least these two equation, it gives you this. I will come to here later. You understand? If we look for radial solution, then minus phi prime of r minus n minus 1 r phi prime of r u are equal to g r. Is that clear? Is that clear?
Yes.
So want to solve this type of equation. Okay, if your domain has a symmetry, your f has a radial symmetry, the given on the boundary has a radial symmetry, all these things are radial, then we can look for a radial solution. Then the equation Laplacian of will be converted. This is an ODE. This problem is turned to an ODE. Okay, now you can study this ODE. Okay, we will see all those things later. Okay, I think now I will stop here. Then we will study this in more detail. Okay, in the next class. Okay, is anything you want to ask me?
Sir,
Ah,
see, if we consider the problem Laplacian of u equal to 0,
ah,
then that the ODE will be converted like phi double prime of r plus n minus 1 by r phi prime of r equal to 0.
exactly,
And so we can solve this ODE. And
exactly. This will immediately
and does
solve.
that mean that every harmonic function will be like the solution of this solution of this ODE?
This here I say that I have convert this problem. So what I said, we look for a radial solution. If you say that what are the radial harmonic functions, Laplacian of u equal to 0 in Rn, then you could say that these are okay. Okay,
Yes.
but not always you have. What I said, see here I will, if we look for radial solution, then this. So Laplacian of u equal to 0 in omega. This omega can be very bad. You don't know what is omega, right? We not have a radial symmetry.
Yes. Yes.
Then you cannot seek this solution also. But one solution, this in Rn, this Rn has a symmetry, right? Rn always, if you any T of Rn, if T is an orthogonal group, orthonormal matrix, then T of Rn is Rn, right? You know that, right? If it is an orthogonal, if there is symmetry, then one can look for a Laplacian u equal to 0. You know that in Rn constants and linear functions are also, they are not radial, right? Like summation ai xi. These are the solutions for solution for Laplacian of u equal to 0, but they are not radial, right? Yes. But
Yes,
you
sir.
can say the Laplacian of u equal to 0 in Rn. What are the radial solution of this equation? We will do in the next class. What are the radial solution of this equation, Laplacian of u equal to Rn? Then we will see that there are you can solve this ODE. But these are only radial solution. That does not mean that there are many other solutions. Okay, we'll go to that. Okay, clear?
Yes, sir.
Good. Is anything else?
And so here we are taking minus Laplacian.
Why I am taking minus Laplacian? This is something we will see later. If you don't like minus, you take Laplacian. This is some convention we use, some physics convention. We will tell you what is the why I am using that. Okay, I will tell you why I am taking. This is a convention. One. I will tell you next class why I am taking minus one. Okay,
Okay, sir.
I will tell you. Minus is the not to bother you. This doesn't bother you much. For harmonic function, minus Laplacian equal. But when I am writing Laplacian equal to f, always start with the minus Laplacian equal to f. Okay. There is some reason I will tell you why I'm always because if it is f is 0, Laplacian equal to 0, then minus Laplacian of u is also, so minus doesn't matter. But when I'm talking about Laplacian equal to f, then minus Laplacian of u f has changing sign, suppose, then this minus plays important. I will tell you why minus. There is something related to function analysis. I will tell you. It's very simple, very simple. I will tell you why I'm taking minus. Okay. Next class I will seek for radial solutions of the equation Laplacian u equal to 0 in Rn. What are the radial solutions? Okay. And with that we will study Laplacian u equal to general f may not be radial. Okay. Then how to study that? We will see that, all those things. Okay. Okay. Is this anything else? Anything else? Okay.
No, sir.
Thank you. Thank you. Let's meet next on Thursday.